This is part two of chapter 7.1 lecture. So your note sheets, have them out, and we'll continue on where we left off. Um, we're at the bottom of the second or bottom of page one. And so the first idea that we talk about is this idea of something called a normal curve. We've been drawing these curves already. We've just been calling them bell-shaped or symmetric. And so when we have relative frequency histograms that are symmetric and bell-shaped, very key ideas within the course so far. When we make graphs, they tell a story for us about the data versus skewed data. So if we have data that's bell-shaped and symmetric, we now are going to use the term normal curve. It has the shape of a normal curve. And so what we're looking at here, to fill in our note sheets real quick, a continuous random variable is normally distributed. There's again the keyword normally distributed, or has a normal probability distribution if its relative frequency histogram of the random variable has the shape of a normal curve. And there's the key thing. Now, what is a normal curve again? A normal curve is bell-shaped, and it's always approximately, not always perfect, and symmetric. So that's what we're talking about. On the next page, we see some examples of a normal curve and the properties of a normal density curve, because we're going to be using these to solve probability problems. Normal density curve. Again, density and the idea that we're going to solve probability problems using this curve. And so important characteristics, bell-shaped, symmetric. There's a point here that if you've had calculus, you might have remembered. This is called an inflection point. It's where the curve kind of changes its direction. And so at that point is where we would mark off the first standard deviation, and then we have our second standard deviations, and that's what that's labeling here. And so normal curves are symmetric about the mean, meaning the average or mean is always in the middle. Mean, median, mode are approximately the same, right, at this value here. Again, this is a relative frequency histogram that we're drawing a curve over, and we'll take a look at what I mean by that again. Inflection points, where the curve kind of turns. This is where the first standard deviations would be. The total area underneath the curve is 1. And so that's the idea what we're talking about with respect to a normal curve. And let's apply this now. We're going to connect this idea to what's called the empirical rule. We know about the empirical rule, but when data is bell-shaped and symmetric, we can apply the empirical rule. And the empirical rule you've learned before with a normal distribution. We have these percentages of values that fall within 1 standard deviation, 2 standard deviations, so forth. There was actually a question on exam 2 about this without applying the normal distribution ideas, just the empirical rule in general. And then we have other kind of examples here. Here's an example of 2 curves that have different means but same standard deviations. You can see the spreads are the same. And here are 2 curves that have this different means but same standard deviation here. So you can see the means are not equal, but the standard deviations are. Shapes are identical. The means are equal here, but the standard deviations are different. One's more spread out. And so we have this information here. So let's look at an example that applies the normal distribution. This is from the PowerPoint. We talk about normal curves. We talked about what does a normal curve look like. Some of the characteristics. You have that on your note sheets, the properties. Make sure you read them and try to understand what that means. We can apply the empirical rule to normal curves, this is something you should understand, know, memorize, all of those things. Try to create this yourself, and then understand the distribution of percentages. And what this is, again, is what percentage of the people are within 1 standard deviation of the mean below, what percent are above, and so forth. And so looking at this example, which is on our note sheets here, you're going to see data for 2-year-olds. So this is data for, this is 2-year-old males. This is their heights. And so this is unorganized data, raw data here of 2-year-old males. What do we do with raw data? We go ahead and make a histogram. So this is raw data. We take the raw data and make a histogram. This is a relative frequency. So what does that mean here when we look at this? So what does this bar right here, like what does this bar here mean here? It looks like this bar, this height that is at 20%. So to me, it looks like with this bar right here, what does that bar mean? That bar means that 20% of 2-year-olds are between 34.5 and 35.5 inches tall, right? And so that's the interpretation. We make a histogram, and this bar represents the percent of people, 2-year-olds, that are between 34 and 35. That's what that bar means. And so what we want to do is we want to connect this idea. Hopefully that makes sense. So again, stop and make sure you process that, understand where I got 20% from. It comes from right here. And then what we want to do is connect this idea to how does the area of a rectangle relate to the area between the curve, right? And so how do we connect area to probability? And so that's what we're going to be looking at here. So on your note sheets, you also have this picture here. So what we do, and here's the key thing, in this class, we're going to draw normal curves all the time, right? It's going to be something we see all the time. And so this normal curve, though, is just a shortcut way of drawing a histogram. We just don't want to draw all the boxes. And so that's the idea of where we're going to be drawing normal curves over and over again to represent histograms and represent data. And so in this case, instead of doing a histogram, we could have just drawn a normal curve over the top of it and then say there's the distribution of the heights of 2-year-olds. That's what we could then say. And so looking at our note sheets, what we have here, so we have this data was made here. And so using this information, we can then go ahead and answer some questions on our note sheet here. One is the area under a normal curve. Suppose that a random variable x is normally distributed, which we have here. We're rarely going to be drawing the histogram. We'll just be drawing the curve. The area under the normal curve represents either the proportion of the population with the characteristic described or the probability. So remember, here's the key connection here. The area under the normal curve is going to be connected to the proportion of the population or the probability, right? That are randomly. So this is such an important idea here. I don't know how to highlight it anymore. So other than to say important, okay? So I'll repeat that. Somehow you have to understand this idea. Understand this, important to understand, okay? So think about what that means here. So for example, now I can then calculate this here. The probability that a 2-year-old is between 34.5 and 35.5 is going to be the area underneath this curve here. How do we find the area of this rectangle? It's going to be the distance from here to here. So we end up with this rectangle. It looks like this. It has a base of 1 and 0.20 on the top. So this answer is 0.20 because we're going to do 1 times 0.20 equals 0.20. So that's what we're going to do. Now, we're not going to do this by hand. We're going to be doing this using StatCrunch, though. This is just the example that we're first doing. And then when we get to StatCrunch, you're going to see this is what we would be doing. We just hard to do this by hand all the time without the rectangles. So let's provide one example before we finish this lecture. Um, the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds. And so what happens is this. You've done this before. In the middle will be 2,200. And then we label standard deviations here, 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 here. It's 200, so this is going to be 2,400. This is 2,600. You've done this before. Here's the mean. This is going to be 2,000, and this is going to be 1,800. We'll do a third standard deviation. So this is 1,600, and this is 2,800. And then we recall, how do we draw a normal curve? A normal curve here has inflection points at the first standard deviation. And so then we want to then draw a normal curve now. Let's do it in a different color. Here is the mean. Here is one standard deviation. So I know we're going to have a curve somehow here. I'm just sketching out a normal curve because I don't have all the data. I just know it's normally distributed. And so then you end up with a normal curve that looks like this. Just like that. And so this is, this represents the weights of giraffes. And it's a relative frequency. We're just not drawing all the rectangles in. I don't have all the data. I just know that it's normally distributed. Because I know it's normally distributed, it's going to look like this shape. Its histogram would look like that if I had the data. Okay, if I had the data, it would look like that. You got to pause and think about that again. So draw a normal curve with the parameters labeled. Just did it, right? One standard deviation, one standard deviation below, two below, three below, and so forth. Part C, shade the area of the normal curve to the left of x equals 2,100 pounds. So let's go ahead and find 2,100. Here's 2,100 right there. And what does that area look like? It looks something like this here. This is the area in green. So shade the area. So I did that. Suppose the area under the normal curve to the left is 0.35. So in this case, 0.3085. I mean, let's say we calculated that. Remember, there's no rectangles here, so we can't do these calculations. We got to use technology. In this case, it's given to us. What does this number mean? Pause, think about it. What does this number mean right there? Okay, let's go back to this right here. The area under the normal curve represents either the proportion of the population with that characteristic or the probability that a randomly selected individual from the population will have this characteristic. And so what does 0.35 mean? What's my interpretation? What this means is that 30.85% of giraffes weigh less than 2,100 pounds. That's what that means. Can't fit the word pounds in there. Weighs less than 2,100 pounds. That's what this area is. Another way would be to say, what's the probability that x is less than 2,100? It would equal to 0.30. Probability of what's the probability that a randomly selected giraffe will weigh less than 2,100 pounds? It's 0.3085 or 38.5%. That's it. We'll talk more about it.